Welcome to another video on the TinyGo code review. Today we're going to be reviewing some source code of the Gopper project. So this project is a Clipper firmware implement. Oh, I just noticed you are not able to read. So this is a firmware implementation of the Clipper protocol and ecosystem, so as to say. So it's got full Clipper protocol compatibility, written in TinyGo. I mean, really, it's not written in TinyGo. It's written in Go, compatible with TinyGo. It'd be compatible with TinyGo for optimal embedded system performance. And I'm about to create a branch for my suggestions for this repo. And note, this video is not sponsored, so as to say, but I am being paid by Amkin to work on their repos. They did not specifically ask me to do a video on their repos, but I thought, hey, if I'm gonna be coming face to face with this repo for the first time, I think there's a huge value in recording my interactions with this repo at first. So I've already looked at the repo a little bit and already have some thoughts, especially in the protocol section. So yeah, let's look at this. This looks like AI generated readme right here. Your classic AI generated readme, very repeaty stuff. It's like just the only thing. Oh wait, there is something that changes. Build targets RP24. Okay, so it does note there are different targets. I'd call these examples, right? Because you can always design. Oh, and this doesn't exist, right? Targets. Okay, this might, I guess this is hallucination, AI hallucination. All right, so odd readme. Maybe I'm missing something. Any. Okay, so there's this like language for C test for more example configurations. Okay, so we have configurations. Nice. So there's gotta be somewhere that reads. Okay, this must interact with the Clipper. Okay, but it's not using a Clipper library. Interesting. It's just a Python implementation. Cross. I don't know, why wouldn't you write this in Go, right? Because maybe you like Python. Let's continue with, I think the most interesting thing to note here is, I guess, a tiny compress library, which implements zlib. So I think there's lots of interesting stuff here to read. Minimal deflate compression, right? And this looks very, very nice. You know, I think I'm not going to spend too much on the zlib encoder, decoder, because these look quite good, you know. I mean, it does. Is this an allocation? So output. So I guess quart size to the stream. I guess it is pos 0. Yeah. So this just writes to the stream. It looks like it's not writing to a stream. It's just returning a byte slice, reusing the byte slice it had there on the encoder output. So this is not great because it's not documented that another call to write block just obliterates your previous work done by write block. So this should definitely be an argument and fail if it's not enough size. Yeah, or unexport it and work with it with internal assumptions, of how write block works, where it just overwrites your output buffer. But yeah, this could lead to some very hard to debug bugs on the user side. Compress. Sometimes in the effort of making your library heapless, you sort of fall into these patterns which might, they might look sound at a glance because, okay, look, my memory is bounded because there's ways of really running out of memory if every time you call this library you're like using a slightly bigger buffer, a bigger input, or a bigger required size. No, input plus 7. Yeah, bigger input buffer, so you end up allocating until you run out of memory. So this looks like a case ripe for, input output, right? Because yeah, you're trying to make it heapless by doing this. You're missing the part where you bound your memory growth, and you also don't hold a reference to the buffer, which you overwrite. And if you do, document it as such, because this library would be kind of just not comfy to use in its current state. So I'm probably going to take a look at this and make it better. Encoder. So it's using the same buffer for everything. So this is, yeah. This is going to cause some problems to people who, think, oh, this is an allocated buffer, unless you read the data and see it's part of the encoder. So I've already found things to improve in zlib, and let's see protocol. And that's really the only thing I'm noticing is sort of off here. The rest looks really nice, you're composing your encoder with your decoder. Here the stream uses its internal encoder, so you can like share functions. So I guess you're just including the encoder so that you use the buffer. Yeah, okay, I'll probably improve this library quite a bit, and because it's just, all you gotta do here is, make output, right? Delete this. They're both byte buffers, so just do that. And you do the same thing for, also, I'm not gonna delete, it's got 2 buffers. So this is probably the auxiliary buffer. It's used for uncompressed data. Although here you're using it for decompress. What? Decompress. That's an odd name for a function that copies compressed data. Or this is just like compressed. You grab your compressed data and you copy it to buffer, and then you say it's decompressed. This is odd naming. I'd call it like unpack, maybe, because you're not really decompressing in the sense of uncompressing. Or maybe maybe unpack is synonym to decompress in the archive and compression world. Decompress stream seems like it would do the same thing, except in a for loop. Is there such thing as? So is this doing any compression at all? I feel like it's only packing bytes in. No compression. Okay, so this is a library that's just zlib. It's just zlib compatible, but with no compression. Okay. So it's decompressing, but performing no compression. Like decompressing, no. Okay. Anyways, my original statements are still stand. I do input output, and instead of having this guy, we do that and just replace output everywhere. And here we return cap. We can do append compress. And usually in the append, the output is on this side. I'm not going to go ahead and actually implement this, but just show you what I mean. I'll do it later and put the link to the PR in the video notes. But basically this, destination, st, and 0, error. I don't know, some error, right? No, I can't compress it, or this would be short buffer. Maybe? Yeah, short buffer. Since we're like reading from the input. Yeah, that's what I would do. And then just replace all the outputs with output. Oh, this would be pause. Just bam. Oh, output, dst. And this is probably what it's going to look like, right? I still have to, okay, here it resizes it. Yeah. Pause is going to be required size plus 4. And I guess we can, if pause is not required size plus 4, panic, right? We're not going to panic. We're going to return an error. Panic sounds better because this is likely programmer error. If we don't match pause with required size, something's way off. All right, that's going to be later. So that I'm going to do that on my own time because it's literally just apply this change to every single function here. So let's move on to protocol package. So the actual protocol stuff. Okay, so this is a Clipper message block. When we're talking about Clipper, we're talking about a protocol that occurs over some sort of form of I/O. Could be UART RT, WART, SPI, could be TCP. You know, it's just some form of exchanging these messages, is what I imagine. I'm completely new to Clipper. The README, Clipper, so Clipper protocol. Oh, do we have anything else? Scheduler. So protocol contains all the Clipper stuff, and that's really what I'm most interested in reviewing, because it's going to be relatively simple compared to doing some heavy embedded stuff like target dependent logic. So yeah, let's just look at protocol and the rest of this stuff. So yeah, I did look at this before, so I already know what I'm about to say is why. Clippers encoding. I like that you match Clippers encoding. I don't like how you've defined this sort of abstract output buffer type. What is an output buffer? So you have output writes data to the buffer. So boom, this is write, equivalent of IO writer, right? Writer 2 would be write. Writer 2? Writer 2. No, it would be write. Or read. You're encoding, so it'd be equivalent of read. You know, this is written to the receiver. In this case, the receiver is this output buffer. Output, output, output. You're outputting this VLQ integer, variable length. So it's probably some variable length integers. VLQ integer, yeah. Variable length quantity. So these are just, MQTT does this very similarly. You have the way you represent integers over the wire is by having integers that are variable length. You know, at most 32 bits, and at very least a single byte. 8th bit is continuation flag. So when the 8th bit is set, you know, you gotta keep outputting stuff. And here we have, yeah, I guess this works. Okay, it's setting that VLQ flag. This is the continuation flag, and the last one is just the byte. So if the number is smaller than 128, it should not run into these. But if it's larger, it's gonna run into more. And then you have current position, update, data since. So let's continue reading this. I already have an idea of what I'd want to change. New scratch output. So this is a buffer implementation. So you already defined the message max size here. Yeah. I'm not liking this. So much abstraction. S.pause. So there comes a point where output's not going to output any more data when you're past the message max size. It's, curious, you've defined it here. You know, you could define it as I guess it's a bit more, if you're gonna want to limit the size of your, no, I mean, you could just have this be a slice, so you can do variable length, not have a single have a variable message max size. But you know, that's not my real problem with all of this. My real problem is way too abstract. I feel like this is much more complicated than it needs to be. You know, this is really just a buffer. That's just a, why not something like output buffer struct buff update? Not even this. I mean, you can look. It's just so odd, you know. I find this, maybe there's a reason. You know, in Go, it's very common to find these sort of abstractions. You don't have to go too far. You've got a gold mark. So trophy. Oh wow, Ewan just fixed number 541. Nice. So here we are at Goldmark. And so this is another library I feel could have been, it's a great library, don't get me wrong. This is a very well-designed library. It's very flexible, it's beautifully done. However, maybe I would have designed it differently. I'm sort of big on I like simpler stuff. Let's see if we can find some of that code I'm thinking of. Yeah, here we go. Convert. So it's a bytes.buffer. Maybe this is not what I'm thinking about. Okay, that's a WhatsApp message right there. I thought there were more. There was like a gold mark abstraction for the buffer. Maybe that changed? Is this on version 1? Maybe I'm thinking of an earlier version where it wasn't a byte stop buffer. It was like its own... No, I know. Here we go. This... Because I've worked with this library and should be here. No register. Here we got util. Yes, yes. So I had to work with Goldmark. I had to implement a util buff writer. Not implement, but you know, that's what I receive. And dude, like, can't you like use a bytes buffer or buff.io writer or something, or just a writer, you know? This will be faster than just a writer and simpler to use for users because it will have nice methods. So maybe a writer is not the best case, but I'm thinking because you're gonna want to maybe limit the amount of output you can generate, so that you know you don't DDoS yourself with an extension, because this is an extension you can put extensions into your library. But I do feel like there's a better path forward than just like, hey, here you go, have this buff writer. Yeah. Although, as of now, I don't know, it looks like you can pass in maybe the writer's wrapped. Maybe Goldmark receives a writer and util buffer. But I'm way off track anyways. This was not what I wanted to show you. I just wanted to exemplify, hey, sometimes a byte slice is what you need. You got a length there, you got a capacity. Maybe you design your API to not append past the capacity. In this case, you don't need extensions. So you can say, okay, I'm gonna append to the output buffer. But if the amount of free space is too low to append to, that means we're not appending anymore. That means, and you get basically the same behavior as the scratch we just saw. Scratch output, you know? You got your buffer, your position is now your length, and your capacity is the max size. So yeah, I'm not a fan of these abstractions for protocols, for working with data. I think there's better ways to, I mean, if you're working with, native Go, then yeah, go for it if you like that. But if you're working on embedded systems, these are like expensive and they should be inexpensive calls. You should be able to put data straight into a buffer, read a byte at a position without calling a virtualized method. Like, why are we doing that? But hey, this is gonna work. So not a fan, but it gets the job done. And it looks nice, because, it's nice and packaged. It's implementable. But if we continue, we find that this is a pointer to a byte. So now we've left the land of the output buffers. Now we're decoding. And now we're decoding from, so you're modifying the byte slice. Is advanced past the consumed bytes. Yes. So this is an interesting approach to decoding where you use the byte slice, you modify the byte slice, right? Pointer to a slice of bytes. Why don't you just return the amount of bytes consumed? I consumed 2 bytes. I consumed 3 bytes. This is how the UTF-8 package works, and I feel this is really nicely implemented package. You got your rune, got your size, and yeah, you can decode all you want. And interestingly enough, I think you can implement. So notice how this doesn't have an error returned, and this can fail. How are you gonna know if it fails? Because rune error is returned. So UTF-8.rune error, and that's a constant rune. Boom. But I can't do the same because I'm decoding variable length. I think you can do the same. Pretty sure there are non-representable. Yeah, you for sure have non-representable integers. You could do const VLQ error is 0xFF. And this is not representable as a VLQ. You can't represent this as a VLQ because the continuation flag is set on the last bit. So you're telling the implementation to continue past, the maximum size you can represent as a VLQ, which is 4 bytes, apparently. So you can actually implement a function that matches the UTF-8 package here. Decode VLQ. And this is redeclared. But yeah, this is not representable as a variable length quantity. So you can implement the same identical signature. This is a VLQ and this is amount of bytes read. And you do without the errors, the error type. It, of course, requires documentation and for the user to understand how to use it, but the user is probably not going to be like decoding VLQs. The user is going to be, using this transport type and receiving messages. So I think that would be a welcome change. And if the user's confused, you can just point them to the UTF-8 rune package, which works wonderfully. Heapless and simple. And if you really want your integer, then just use this. I mean, if you really want your error for explicitness, then just leave it in. But yeah, that's decode rune would be the... Continuing, what else do we have here? So what I'm thinking is, the rest is pretty much straightforward. It's just the same. Pretty sure what I'll be doing is just doing func encode VLQ. How does the UTF-8 package do it? Encode writes. Okay, and rune error is written. I don't like this. I would like this to return an error. But yeah, return an error is probably for the best. Because UTF-8 does differ in some things, like it can represent a 1 byte. So is UTF-8? I'm getting kind of off track. This is what we're gonna do. We're gonna do func encode. Encode VLQ 2 and DST bytes and the value uint32, because that's what the binary package does, unsigned ints. And then we have amounts of bytes written. Yeah, we can return an error. Let's not skimp out and implement that. It's going to write into the bytes. It's going to say how many bytes it wrote. Then we're going to have encode VLQ decode VLQ2. We're going to have it's going to be source, and we're going to have uint32. And if it's a signed integer, you can just convert it to signed. It's to int32 straight up. And this is going to return the amount of bytes written, and if there was an error, it'll return the error. Yeah, I guess we could almost do without that. Yeah. If error, then return VLQ error, comma, -1. So the user doesn't check, it panics. You kind of force a panic on the user side, because that length is going to be used to index, and you're going to... Or maybe do like... if error, if bad, then you do this. Make sure the user's checking this. There's several ways you can design this API, but yeah, that looks decent. I don't know if it's the best. Maybe it's worth including the error. Then there's the command handler, and it works on the data. So I guess this is for receiving, moves the pointer, moves where the byte data buffer is pointed to like advance the read, transport, receive. Data is a byte. Receive. Isn't it like modifying this data buffer anywhere else? It's just advancing it, getting data. If data is less than message length. Get the data. It doesn't seem to be doing anything with the data buffer. That's odd. I thought this would be calling on the command handler, which modifies it, but nope. What about, that's the receive. Okay, we know that's receive. Parse frame. Recover. In command handlers. Yeah. I mean, it's fine. You should strive for no panics, but just to be sure, put a recover in there. Yeah, that's good. Aha, here's the... Okay, here you advance the frame, and here you advance the frame in parse frame. Parse frame is used in receive, and frame was generated from data. Okay, That's how it works. I think this logic could be a bit more straightforward. Nothing much to say. I think the overall concept is good. You're like working on it, chipping away at the frame until you finish it. Is there a need for a command handler? No, when are you... Okay, here's a new transport, and what are you passing in for a command handler? Okay, this is never instantiated. I do wonder, like... CMD ID, okay. These are arbitrary commands. Right, okay. Input buffer. Data. So, I do understand why you're using an input buffer here, because, hey, you might not have all your data yet. You know, you might have available this data. Pop removes n bytes from the front of the buffer. This can be made much simpler. And the only reason I know this can be made much simpler, just work on it, is because I actually, or just more according to my tastes, if you will, because I've implemented HTTP for microcontrollers. And I have something, I've arrived at an implementation of HTTP header parsing, which I really, really like for like working on, you know, incomplete data. So HTTP, if you're not familiar, you establish a TCP connection. One side, maybe it's the client which is reaching out to a server, says, hey, let me get this page. And the server replies with a HTTP response, just a string of bytes. I mean, they look this way. I don't have an HTTP. Am I really gonna search HTTP with header example and HTML? Because, you know, usually you do HTTP and this. So this is what the HTTP header looks like. And then usually you don't only have the header, you also have... Oh, right, this is the response. Sorry, so this is what the client sends. So blah, client sends this. And then what's interesting, if you as the client are reading from a TCP connection, which might not send entire data in one packet. So you might have bytes, but those bytes might not be the whole entire message. So that's a big problem, because now you have a situation where you have... Maybe you just have part of the header in one TCP packet. Maybe the header's huge, or maybe it came in chunks, and now you have just this part of the header and this part, and the next packet receives this part of the header. What if you first read this? You gotta make sure that you're keeping track of what you're reading and building it as you go. You know, you're reading, new data read is sort of accumulated into your own HTTP buffer, your structure that's reading from the HTTP, and you can kind of tell when part of the message is complete and be able to parse that partially sent line. So if it sent this line up to December, you got, I'm missing the new line. So I gotta wait until I get the new line before I continue parsing. So maybe you parsed all this and then your implementation said, hey, this is not done. I'm still waiting on more data. And that's when you get an error. Need more data, cannot find trailing line feed. So HTTP famously requires a trailing line feed for it to work. So it's got to end on 2 trailing line feeds, right? For it to be a proper message. For it to be a proper header, sorry. This has 2 line feeds, right? 1 line feed to get to the next line, and then another line feed before the actual message begins. So this is the header, and this is the payload. So whenever you get the need more, you know you gotta keep going. Empty URI, parse first line response. So I'm looking for the actual exported methods. Maybe it's these. Parse bytes. It fails. So this parses a byte buffer. Okay, you have all your data. But there's also this try parse. I found a really nice pattern. You know, you got your header, which has a source, presumably. Parse next headers? What? Scanner state. Next. So... try parse. Read from limited. So read from bytes. Okay, you have to use try parse in sync with read from bytes or read from limited. And this will read from the reader, fill up the header buffer, and then after calling read from limited or read from bytes, then you call try parse. And if try parse succeeds, you can be sure that it parsed no error. If it has no error, then you know, finished successfully. But if it fails, and if you get this Boolean flag tipped off, you know, hey, I failed, but there's more data. If I get more data, I might be able to successfully parse this. So you get this sort of state in your header where you've partially parsed your header, and you're still waiting on more data before successfully parsing. And you can after calling try parse and getting a need more data Boolean, you can continue reading. And I think this would be a pattern that Gopper would benefit from greatly in cases where you have incomplete data, like maybe a WART port, a serial port, or even a TCP connection, much like in the case of HTTP. So I'm thinking I'll probably add these methods, probably add a method to maybe message. So one thing to keep in mind with Clipper, same goes for HTTP, is after receiving the message, parse frame, cmdid. If len of frame, and this is called from here. Message, do we have a message type here? Receive. So I'm guessing all this does is call the callback in parse frame. Interesting, they ignore the error here. Next sequence. So what's all this expected sequence stuff going on here? I find this odd that they're segmenting sequences. I mean, are you really gonna have like multiple input buffers? So I'm kind of confused now because I'm seeing some sequence length in here, and it's like an atomic integer which is loaded. I expect this expected seek message test. Expected seek is message test. If seek is message test, message position sequence. So not sure how this is gonna play in concurrent setting, because I assume that's why he's doing they're doing this sequence loading and storing. How is this gonna play in the concurrent setting? Because you've got, I mean, it's synchronized. This is odd. It's very odd. Get synchronized. I'm not liking what I'm seeing with respect to that atomic use. I mean, it's not like it's a bug or anything. It's just like, is this meant to be? I wasn't aware this was meant to be like concurrently used. I mean, this looks like a very serial problem. You have your buffer, you read from your buffer. No one else is going to be reading from that buffer unless you have multiple data sources, which would be crazy. That would be crazy. Is this meant for multiple data source use? I mean, we could read the comments on is synchronized, start synchronized. No, next sequence. Let's read the comments for next sequence. Check for host reset. I really feel like it's critical, both ACK, response, right header. Yeah, I think this is overkill. I don't think you need atomic access for your next sequence. You should be calling your receive sequentially. You definitely should be calling your receive sequentially, because or else you're gonna like your handler is gonna be like receive jumbled data. I mean, then you'd want to like maybe make out the difference between the different data sources, ID your sources, add like a ID. Yeah, and that seems like you're overcomplicating. You can define several transports and use one transport for each data source, and that would be a better pattern than to make transport work for concurrent use. I'm definitely gonna remove the concurrent assumption from this repo, this type, and gonna work on leveraging the simplicity of a serial protocol, because as I showed you, you can have something that just saves the state in between each parse, and once it's done, if it is done, it just returns nil error and no more data needed. So that's what you need. And here's an example of how to use it. For need more data, read from the reader, try parse. If I need more data, then read from the over and over. And I mean, you can make this as complex as you want. That's the point, kind of. You know, you make your API simple so that user adds the complexity they need. Maybe they need to make an exponential backoff every time they read. Maybe they don't. That's up to the user, I feel. Also, very clean, nice pattern, this. So I'll probably, I don't know if I'm going to make another video showing the changes I've implemented. I'll just leave a link to this repo and let the results speak for themselves. So thank you for watching. That's it for the code review today. I hope you enjoyed it, found it useful, learned a few things about API design. Bye-bye.